For those that asked, I did not post an intro video for this week. I meant to tell you on Friday, but may have, I know in this class anyway, I had slipped my mind. But we're talking about applications of exponentials. So it's really, and when you look at both the notes and the homework for this week, there's just about, I don't know, total probably maybe like 8 different situations or something that we're looking at. But what we're going to figure out is that we don't really need that much specialized knowledge for any of them. It's kind of using the same idea and then doing, function interpretation in kind of the usual way. So exponentials show up all over the place in modeling any kind of growth. So that growth or decay. That can be money, like the balance of an investment or the value of a loan or something like that. And we'll spend a lot of time on that. That'll probably be about the thing we spend the most time on today anyway. There are other places, radioactive decay, Newton's law of cooling, like the way a warm object cools down in a cooler space, or vice versa, warming up in a warmer space. Those are exponential models. Population growth is another thing that if you look kind of long term, you typically model that with an exponential. So there are a lot of places that exponentials show up. Logs as well. The log examples are kind of a little more esoteric usually. There are things that work on a log scale, like the Richter scale for like earthquake intensity is a log scale. Decibel sound intensity is a log scale as well. So you'll see a couple of those things show up in the homework. But the main thing with a lot of the homework stuff is going to be just keeping in mind how functions work, right? If we know what X and Y are and can interpret, okay, X is time or X is intensity of a sound wave or something. And the function is modeling how much stuff you have, how many people live there, what the decibel level is for that sound intensity. Like that's going to be the main thing. So I would just encourage you, when you see, a new homework problem pop up and all of a sudden it's talking about a whole different thing, to not panic and to just, read what it's actually saying, right? Several of the applications we've done up to this point, like, think back to like test 2 stuff when we were doing quadratics and talking about projectile motion, right? It was, okay, well, X is how far and Y is how high. And like, we just kind of dealt with that same situation, over and over and over again, right? This is going to be less like that. But again, it's all going to tie back to what's X, what's Y. Okay, the function tells me how they relate to each other then, right? Okay. So compound interest. Now again, of all the stuff that we've talked about, we've done all kinds of mathy things that, you might never really need to solve a quadratic equation in real life, right? But, it's about building the critical thinking skills and logic and stuff. The money stuff, this you do want to know about in real life. We are simplifying things a little bit from, sort of the real context of how things work, right? Generally, the places that you really care about money in your real life are going to be, I borrowed money for a mortgage or a car loan or student loans, those kinds of things. Those kinds of like big transactions, you make payments on over time, right? You don't just like let it sit for 10 years and then go pay it off with one check, right? That's usually not the way it works. So the interest works a little bit differently because the balance is changing a lot, right? Like you make a payment, the balance goes down a little bit, they charge you some interest, it goes back up a little bit, you make a payment, it goes down, hopefully more than it went back up, right? So it kind of goes, like this a little bit, right, as you're like paying it off. What we're going to talk about is, just for the sake of like simplifying the calculations basically, is you borrow a bunch of money and then it just sits for, 10 years or something. And then, okay, how much do I owe on that now? Or conversely, I put a chunk of money into a bank account and I just left it alone for 10 years, right? Which is, something like, when you make a long-term investment like a CD or something, that's kind of how that works. You just take a chunk of money, you set it somewhere, you forget about it as best you can for a while, and then later you look and you go, oh, hey, cool, that number's bigger than it used to be. Good, right? That's great. But we're not going to get into the like making payments in like you would for a like retirement account or something like that, or taking money out, right? So we're going to take a chunk of money, we're going to set it somewhere, we're going to see what happens. Now, when you do that, if you take a chunk of money and put it in the bank, what the bank does is take your money and loan it out to other people, right? I mean, basically, like they add it to sort of this like capital that they have that they use to finance loans. And then on those loans, they charge interest, right? So because you're because you're letting them borrow your money, they pay you a little bit of interest, right? To just sort of let it sit there. Now, generally, if you put money in like a savings account or something, that interest is very low, but it's nothing, right? And generally, if you take a loan out, that interest is higher, right? Because the bank's making money too, right? So the way that works is that every once in a while, the more time that sits, the more interest accumulates, right? When we talk about compounding, we're talking about the schedule, right? How often you do that calculation and add to it. So, I take, I don't know, $100 and put it in the bank. And then maybe once a month, bank person, or it's really a computer, right, goes in and says, how much is in that account? $100? Okay, add 1% to it. Right, that's $1, add $1 to it. Okay, now it's 101. A month later, run the same check. How much is in that account? $101. Okay, add 1% to that. The next month, add 1%, right? And so on for as long as I let it go. That's called compounding, right? That interest calculation and adding it on. And what happens is that each time the amount you add is a little bit more. That's why you get this like snowball effect thing happening, right? The same thing happens with debts, right? Credit card debt, school loan, student loans, car loans, any of that kind of stuff, right? And that's why, if we're not careful with things, we get ourselves into trouble with that kind of stuff. That interest calculation can either happen periodically, which is what I was just describing, like once a month, right? Or once a year, or 4 times a year, or whatever it is. It can happen every so often. Or, and this kind of gives us an idea of how continuous interest or continuous exponential growth works anyway. If that interest calculation is treated as sort of always going on, we call that continuous compounding. Anytime we talk about continuous growth, you're going to see E show up. So this will show up in a lot of other contexts as well. If you talk about population growth, radioactive decay, cooling and warming, we'll see E show up there as well. That's kind of why E matters for calculus reasons we're not going to get into. We've got these two formulas then for dealing with money. In both of them, there's a lot of similarities. These are not things you're going to need to memorize. I'm going to add these to the like formula sheet that you've been getting on tests and stuff. So if you need these, they'll be there. In both cases, A is the amount of money in the account after time passes. So it's like the answer, right? How much money is there after 5 years, 10 years, whatever. That's A. P is the principal, which is the amount that you started with. So you borrowed $10,000 for your student loan, that's P. You take $500 and put it in the bank, that's P, right? Principal is the amount that you started with. That's a 1, that's got an E. R is the interest rate. Interest rates are always stated as a percentage, but to do math with them, you need them as a decimal. So 5% would be 0.05, right? Typically, we're going to have to do that conversion for ourselves because, again, they're always stated as a percentage, but you use a decimal for doing math part. T is time in years. You can do that with different things. It doesn't have to be years, but the way we've set everything up and everything that we're going to deal with, it's time in years. And then the only place that they're different is that this one Here you've got an E, as we talked about. This other periodic compounding formula, you have an N. N is the number of times per year that interest calculation happens. So if the bank goes in and calculates the interest and adds it on to the balance once a month, that means that N would be 12, right? So usually we're going to need to translate that from English to how many times per year, and that part's important. That it's per year, right? So monthly is 12, annually is 1, quarterly is 4. Yeah, those are the kinds of things that you're going to see. Yeah. And then notice that this NT in the exponent, that's number of times per year times years. That's how many total times it happens then, right? Which kind of makes sense if you think about it. That you would take this exponential thing, raise it to the power that represents the total number of times you're going to do that calculation, because it's a repeated multiplication thing. Okay. So if you take $1,000 and invest it in an annual interest rate of 4% compounded quarterly, meaning 4 times per year, how much would be in the account after 10 years if we don't make any withdrawals, if we just, sort of let it sit? Take a second, think about, how you would set that up and find it. And also, this would be a good time to grab your calculator and actually, punch the buttons for yourself. Okay. Oh. What has happened? Okay, sorry, I broke something somehow. Okay. All right, $1,000. What is that? That's P. At an interest rate of 4%, what's that? Yep, that means that R is 0.04. Compounded quarterly, so N is 4. How much will be in the account? So what are we looking for? Yep. After 10 years, which is T. Okay, if no withdrawals are made, again, that part just means, we put the money there and we forget about it, right? We walk away. Which, again, is the only thing that we're ever going to deal with in here is, money goes somewhere and stays put, right? Whether we're borrowing or investing. Okay, so T is 1,000, R is 0.04, N is 4, T is 10. We want to find A. Which formula are we using? First one, because we have a number for N, right? I have something I can turn into a number. If we're going to use this, you will see the word continuously show up somewhere, right? Otherwise, there's something in there that tells me what N ought to be. Okay, so A is, we don't know A, right? So leave A as A. 1,000. 1 plus R 0.04 over N. Oh, by the way, if you look at it, this is taking that annual interest rate, dividing it by 4. You're getting 4% for the year, but it happens in 4 separate chunks, right? That's why it's R over N. To the N times T, so 4 times 10. Okay. And what did you get when you punched all that into a calculator? Okay, I hear that some people don't agree, at least. Let's see. 1,000. 1 plus 0.04 over 4. Basically, you can just enter this all in line in most calculators. Up to the exponent is where things maybe get dicey a little bit, right? N was 4, T was 10. Now you can either, if your calculator does the thing where it like kicks up, to the line where you enter stuff when you do the exponent, you can type in 4 times 10 and just make sure that 4 times 10 stayed where it was supposed to be, right? If it doesn't, you might need a set of parentheses, or better yet, what's 4 times 10? 40. You could just do that, right? So it is 1488.86. Money, right? So round to 2 places for cents. So 1488.86 is correct. I don't know if I heard wrong. If you got something in the like much larger than that number range, right? It's because of the way you enter things in the calculator. Hopefully that's like a one-time, kind of fixed thing. But a general idea. Can I ask you to say what you said just a second ago again?
Oh, I got 40,400.
Right, so you got 40,000 something. But then I thought I heard some kind of comment about what this number was. Low, yeah, okay. Yeah, I mean, it's not a huge change in the amount, right? Okay. Well, depending on your level of like how much adulting you've done at this point in your life, that's the way it goes pretty much. 4% is actually that's a bonkers high interest rate on something like a savings account. Like you're not going to get 4%. If you're talking about like again, just like a savings account, like put it somewhere and let it sit, that's going to be like 1%, 0.4% maybe, something like that. 4% is decent for something like a CD or something. If you start getting into like stock market type stuff, you can do a little bit better. But yeah, I mean that's the way it goes. So like 4% is fairly high, and after 10 years, your money has almost increased by half, right? A little less than half of what you had. But I mean that's kind of the way it goes. So that's about what you should expect to see, and that gives you kind of a little bit of a check on, did I do the calculator stuff right? If this number is like a digit longer than the one that you started with, probably something went wrong. But for things I'm going to grade especially, I mean, homework is homework, you know that, but for stuff I'm going to grade, write this part out, because when I grade things, if this is worth 10 points, 8 of them are going to be here. And then, okay, did you push the right buttons on your calculator? Like that's important too, but I don't really care that much, right? So write this part out, because again, if you did this part correctly and then punched stuff in the calculator, like, okay, yeah, you should figure out how to do that differently, but I don't really care that much, right? It's more about the setup and kind of how the pieces fit together. Common things that kind of go wrong other than just doing the arithmetic part. Converting the interest rate to a decimal, right? 4%, so it's 0.04. Again, if you don't do that, if you put in 4 here instead of 0.04, this number is going to be very big. Like that means you're treating it like 400% interest. Again, that should raise some like red flags, right? If this number, if I went from $1,000 to several $1 million, I'm sorry, no, that's not how life works. Generally that, the interest rate thing or just, something going wrong with the calculation is where people, make mistakes here. But first of all, I guess, is everybody okay with sort of the setup? How we got there? Principle, like identifying all the pieces. Yeah, okay, and how to use, or how to know which formula to use here. Okay, and again, you can pretty much take it as you only do this when the word continuous shows up, right? Otherwise, it's periodic, and something in there must tell you what the period is. And then push all the stuff into the formula and go for it. What's different about B? It's monthly. What's that mean? Yep, and it's 12. Other than that, what do you think we should expect to find? It should be in the same ballpark though, right? For sure, right? It should definitely be around the same amount. The interest rate's the same, the amount of time is the same, the amount of money I put in is the same. I shouldn't expect to see anything like radically different. What do you actually get? Okay, $1,490.83. So about $2 more. That's the way it goes. This is a little bit more than that because we did the interest calculation a little bit more frequently. What happens is that, you know, again, like think about this sort of snowball effect idea, right? Like snowball rolling downhill, but like in, you know, the cartoon sense, right? The more often the interest calculation happens, the more quickly things accumulate. So quarterly, doing it 4 times per year, we end up here. Monthly, we end up here. This is a little bit more, not more in a way that I'm going to get like really excited about, but a little bit more. That's what we should expect to see. Okay, and then, and then B, again, the second part B says continuously. So use the other formula then. Continuous compounding on the same $1,000 investment, same investment, so same interest rate. E, 0.04 times 10. Good that far. Somebody give me the rest of it when you have it.
Do you type E into the calculator?
Huh?
How do you do that?
The calculator, you got an E button that's on the, yeah. Yeah, if you're on a TI, it's the like shift or the second for LN. And then again, you can pretty much just type this in like it is, make sure that the exponent stays in the exponent. Say again. Okay.
Why did I get 1,491?
That's right. 1491.82. That's right. Yeah. Same amount of money, same interest rate, same time frame. The only difference is that instead of calculating the interest once a quarter or once a month, continuous compounding essentially means we're doing it every moment. Like I can't I can't break up into chunks, you know, or put on a schedule when the interest calculation is happening. It's always going on, which means n is infinity basically, and like that's actually where E comes from for calculus reasons. But that means that this should be again about the same, but a little bit more because the interest is happening more frequently. Yeah, Morgan.
I'm putting that into my calculator and I'm getting 0.
Well, that's not good. It's not 0.
I don't know if it's
Oh, probably.
That way you can put it in the temperature. Yeah. Life. That way you can enter it in. Just like
Yeah, the lowercase e. Yeah,
that's what
the uppercase e is like a scientific notation thing. Okay, so one, I guess, is everybody okay with like the math part, like how we're setting things up, how the formulas work, and then any other like tech support type questions for the moment? Yes.
When I use the periodic one, it doesn't come out that big, and when I use the continuous.
Oh, y'all just start thinking about take a look at that next problem and think about how you can set that up. So what that's going to do is this to the 12. Then times it. So you want to either multiply it first or throw a set of parentheses around 12 times. Okay. This word operation stuff is going to read that as like the whole thing raised to the 12, and then multiply that by 2, which is why you end up with a number that's got like an extra digit.
Thank you.
All right, let's talk about setting it up. How long would it take for the amount owed on a $2,000 loan to double in an account that charges 3% interest compounded continuously? Okay, so just start, throwing out stuff that you see there. Okay, so we're taking a $2,000 loan. That's P. We want to figure out something about it doubling. That means A is 2 times 2,000. So 4,000. Okay. In an account that charges 3%. So what's R? Compounded continuously, which tells us what? Use the continuous compounding formula, yep. What are we trying to find? T. The question was, how long would it take? The answer to that question can only be T then, right? Okay, so set up the actual equation for me. And just for emphasis, that whole thing is in the exponent, right? It's e to the 0.03t. That's what we need to solve. Borrow $2,000 at 3%, compounded continuously. That's what this says. And we want to know how long it would take, so find t, for that amount to be the same thing as double what we started with, right? Which is 4,000 because we started with 2,000. Okay, so we need to solve this. How would we solve this?
3,000.
Okay, it's an exponential, right? The thing that we want is in an exponent. We got to get it out of the exponent. Divide 2,000. What's 4,000 divided by 2,000? Let's try that again. What's 4,000 divided by 2,000? Okay. Stop saying it again. It's 2. Hey, check this out. This is 2,000, the amount, right? Times this exponential thing. What the exponential thing does, what do exponential functions tell us about? Say growth. Exponential functions tell us about growth, right? 2,000, the amount that we started with, times the amount that it grew. We want to figure out, how long it takes, so t, whatever, for it to grow by double. So what we're really looking for is, when is that exponential thing the same as multiplying by 2? So did it matter that we started with 2,000 and that meant getting to 4,000? As it turns out, no, because the first thing we did was divide the 2,000 out anyway. So the amount of time it takes to grow from 2,000 to 4,000 is the same as the amount of time it takes to grow from, this is the saddest version of this I've ever had. I have $1. But it's the amount of time that it would take for my $1 to turn into $2 would be the exact same as the amount of time it would take for 2,000 to grow into 4,000, right? Okay. Who carries cash anymore, right? Like, I'm just glad I had something, really. By the time I did that and I had like $150 in my wallet, I was like, where did this come from? Like, did I rob a bank in my sleep? I don't know what's happening. Okay, now what? Turn it into a log. What would that look like if we turned it into a log? So natural log of 2 is 0.03t. And then to get t, divide. Okay, so give me t to, I don't know, 2 decimal places maybe. I don't think I said in the question, did I? No, I said how long would it take?
Decimal places?
Sure.
23.10.
That's years. Okay, 23 years. 23 in a bit, but after 23, the bit doesn't matter so much, right? Okay, 3% interest. Again, something like a low risk like savings account kind of thing. 3% is about right, a little bit high maybe. It takes 23 years for that to double, right? That's a lot. Doubling's a lot too, though. So like that's kind of what we anticipate seeing here. That something like doubling again. That's a pretty big growth in the amount. It takes a long time. But that's how it goes. And so here we needed to set things up, right? So we had to read what was given to us. We had an investment amount. No, sorry, it's a loan. Never mind. It's how much we owe. It turns out it doesn't matter, right? The math works the same whether it's money I owe somebody or money somebody owes me. So we have this investment amount. We want to find out how long it takes to double. Again, notice that if I had taken out the $2,000 part for the original loan, we could still answer the same question, right? And the same way. Think about that same question, but remove that specific amount. How long would it take for the amount owed on a loan to double in an account that charges 3% interest compounded continuously? Well, it's still continuous interest. I'm still looking for how long it takes. Still have 3%. We didn't have any specific amounts, but we want to know how long it takes for it to double, right? Well, what we just showed in what we did here and getting to here is the amount of time it takes to double is the same regardless of what the amounts actually are, right? So if there's no amount given, I could just pick my favorite number. right? I can pick how much money's in my wallet. Now it needs to be something positive, right? Something that makes sense as an amount of money, but choose something to go here, right? I have $1 in my pocket. Doubling that would mean how long it takes for it to get to 2. Okay, well, if the first thing I do is isolate the exponential term, it doesn't matter what values I chose because, I mean, 2 and 1's a bad example maybe, but first thing I would do is divide this over anyway, right? Somebody throw some other number out. Okay. Emma's got $6. She's flexing on us all a little bit. That doubling would mean getting to 12. But again, if you're trying to solve that, what's the first thing you're going to do? Divide by 6. And when you divide 12 by 6, you get 2. So keep that in mind because you'll see some problems where, maybe it doesn't give you a specific amount, right? And the first time you read it, you're like, wait a minute, buddy, like I don't have enough information here, right? This is why, though, the time doesn't care about what the amounts are, right? What that amount is doing is really just taking your exponential function and sort of shifting it up, right? It's like a scaling thing, but for exponentials, they're the same. So it doesn't change how long it takes for something to happen. It just changes like whether you're talking about numbers down here or numbers up here. Okay? So with especially like this kind of problem, we'll see it in some other contexts too. If you read something and it's talking about, I don't know, something doubling or tripling or, growing by 50% or whatever, and you read it and you're like, wait a minute, I don't have any specific amounts, right? It's because you don't need them, but we do have to think through, how we could kind of get around that. Okay? Okay. All right. Now let's take a look at that next one then. So now we've got 2 options. You have $2,500 cash on hand. You want to invest because you're trying to come up with a down payment on a car. And you've got these 2 bank account options. A bank called First National, which is as generic as I could come up with, offers 1.7% interest compounded quarterly. And Bank of the USA, no copyright infringement here, folks, offers 1.4% interest compounded continuously. You need $3,000 for the down payment. We need to figure out which account to choose and how long it's going to take. And the one you should choose is probably the one that goes faster, right? Okay, so how could we get into this? 2 separate banks, 2 separate setups then, right? Okay. Take a minute, read through stuff. I'll put the formulas back here so you can see them without having to flip back and forth. And think first about how you would set those 2 things up. Okay, so in setting these up, there's a lot of overlap, right? You have $2,500 saved, right? Again, like that's your cash on hand to invest. So what's 2,500 for both of them?
It's a principal.
It's principal, right? So P is 2,500 in both cases. In both cases, we're looking for time, so we don't know what T is yet, because the question is how long is it going to take, right? So we're trying to find time. Maybe highlight some stuff. That's P. We're going to be finding T. You need $3,000 for the down payment, so 3,000 is A. And then the other things are where the two are different, right? The interest rates are different. 1.7%, so R is 0.017. Yeah, just make sure to be careful with decimal points there. You're sliding it over two places or dividing by 100. Right, so 0.017. Compounded quarterly. So periodic formula with n equal to 4. The other one, you've got 1.4% interest, so 0.014, but compounded continuously. Okay, so how do, there you go, sorry, didn't realize that was cut off. So how do we set things up here? Yep. Okay. And then again, we want to solve for T. The other one, same A, same P. It's continuous, so E to the 0.014 T. I was highlighting T. There we go. The actual solving part for both of these is going to be pretty similar, right? What's different? The interest rates are different, yes. As far as like what happens when we solve them, it might be easier to see here. What are we going to do to solve this? Divide by 2,500, right? Similar to what we did on the last one. Divide, and then you've got e raised to a power equal to something. Rewrite it as a log. The base is e, so natural log. Here, this is a little bit messier, right, to write down. But this is still just some number. This is still just an exponential thing. To solve, I need to divide by 2,500. Rewrite it as a log. It's going to be a log with a different base, though, right, whatever this stuff is. Okay? And this would be a place where, use your calculators, like memory or whatever, however you need to sort of store this whole number. Like, don't round it in the middle. If you round it in the middle, you'll probably be off by enough at the end to be, wrong. So, hang on to that. But the only thing that's really different, you're going to divide, you're going to take a log, you're going to finish solving, is that the base of the logs will be different. Okay? In either case, it takes quite a while. I'll leave that for you guys to, finish up this evening, and we'll talk about it tomorrow. We'll start with that. I wanted to mention real quick, just on the subject of, adulting and living life and stuff, because I just got to take a loan to put in new HVAC, and dang it, 12-month no interest, right? Awesome. That's great. I love that I don't have to pay interest on this for 12 months because I need to borrow a rather large amount of money, right? The number I blocked out has 5 digits to it. Yes, right. It's fun being an adult, kids. So 12-month no interest. Awesome. Great. But then the fine print. After that, 10 years. That's a big number. Okay? Something like a mortgage, I think the interest rate's maybe around like 7% now or something. Car loans, you can usually get 5, 3, maybe if you have good credit. 15%. And hey, here's a fun fact about this 12-month no interest thing. If you don't have the balance paid off on day 366, they charge you back interest on that year that's already happened. Read the fine print, right? Because the people who loan you money, they are generally sharks. They're not typically nice people. The ones that are like controlled by the Fed and stuff to some extent, like home loans, that kind of thing, like very closely regulated. So those aren't as aggressive, I guess, maybe. Shorter term things, like home improvement loans to some extent, payday loans, title loans, credit cards, those kinds of things, like they are out to, eat your lunch and, make you pay for it at the same time. So be advised, be careful. The money is not the thing that we're supposed to like focus on. That's not where our lives should be directed. But if you get in a bind in that situation, it becomes harder to, live your life in a way that is, glorifying to God and builds the kingdom. If like the only thing you can do is be sort of subject to your the people you owe money, right? So, be advised and just kind of be careful about how you choose to do things in life. Sometimes you got to do what you got to do, but just know something about the stuff going on in the background. Okay? All right, that's it for today. Y'all have a good day. I'll see you tomorrow.
What company was that?
Hang on just a second.
Where do you want us to put these?
Oh, yeah. Turn in that quiz on your way out.